Here we're going to apply the process for drawing force diagrams along with motion diagrams all into one problem. And we have to look at these problems holistically because both things are going to be important, forces and motion. So if we look at this, we have an elevator car that is traveling down at 12 meters per second and eventually comes to rest at the 5th floor. So to begin with, we're going to look at the elevator itself. So on here somewhere, I will draw an elevator. And yes, that works quite well. I'm going to draw the motion of this, so we know the initial velocity is 12. Okay, there's my initial velocity arrow. And it's slowing to rest. So if I have V1, V2, and V3, okay, my change in velocity is going to be directed upwards. Now that I have drawn my motion diagram, I want to be looking at the elevator itself. So I am going to circle the object of interest, and next to this I'm going to draw a force diagram for the elevator. Alright, I'm getting slightly better at drawing these things. Now looking at my motion diagram, I know that the interactions with this are going to be the Earth, so I'm drawing an arrow down. This will be the force of the Earth on the elevator, which I'll abbreviate ELV. And I see that in my motion diagram, my delta V arrow is going up, which means that the force of the cable on the elevator will be larger. Okay, so my unbalanced force is in the direction of the delta V arrow. So it's the force of cable on the elevator. As you can see, I had put a positive sign and a negative sign in for directions, and I added the initial velocity, initial position, acceleration, time, final velocity, and final position. Since forces and motion, there are relationships across both ideas and one can influence the other, it's important to use both at the same time. So we're going to fill in the information that we can figure out from the problem. Since the initial velocity is pointing down, it will be negative 12 meters per second. So I'm going to fill that in here. Okay. The acceleration, we do not know. The time, we do not know. All right. The final velocity, it's coming to rest, so we can write in 0 meters per second. And if we look at the positions, we know that it takes 15 meters. So I'm going to call xi 15, which means if I call xf 0, we know that it is still consistent with our signs and heading in the negative direction. All right, now to apply Newton's second law. Come over here. We have the acceleration is equal to the sum of the forces over the mass. Now, looking at this, we know our acceleration is pointing up, so it's going to be positive. And we have the sum of the forces. We have two forces, so it will be the cable, force of the cable on the elevator, minus the force of the Earth on the elevator. Divided by the mass. Alright, it's asking us to determine the force that the cable exerts on the elevator. So I want to solve for this guy right here. So we're going to take this and we'll say, alright, the force of the cable on the elevator minus the force of the Earth on the elevator. So we found out today in class that mass times 10 newtons per kilogram will give us the force of the Earth on the elevator is going to equal, now what I'm going to do here is I'm going to multiply m by the acceleration, so I'm getting rid of what's in the denominator, is equal to the mass of the object times a. Alright, now since I want to get the force of the cable on the elevator, I'm going to add m times 10 newtons per kilogram to each side. We find out that the force of the cable on the elevator is equal to ma plus m times 10 newtons per kilogram. All right. So the only thing that I don't know is the acceleration, which means we're going to go over to our motion diagram and our motion information and determine. Looking at this here, we can determine the acceleration by using the VF squared equation. Okay, that's a little sloppy, but you guys can figure out what that is. Alright, so I can rearrange the VF squared equation to solve for the acceleration. So I get VF squared minus VI squared. I subtracted VI squared from both sides. And then I divide through by 2 delta x. That will equal my acceleration. Alright, so substituting all the numbers in, I have 0 squared, which is going to be 0, minus negative 12 meters per second squared, divided by 2 times, and this is important, it's 0 minus 15. Okay, so when we look at this, we're going to end up getting a negative on the top, negative 144, and a negative on the bottom. We divide the two, you're going to get a positive 4.8 meters per second per second. Okay, now we have our acceleration of the elevator that we can use in Newton's second law. So we'll go back and solve for the force of the cable on the elevator. Okay, so I come here, we have the force of the cable on the elevator. This will equal mass times the 4.8 meters per second plus the mass times 10 newtons per kilogram. If we substitute the mass in, we're going to get 720 newtons plus 1500 newtons. All right, that will end up equaling 2,220 newtons would be the force of the cable on the elevator. All right, box that and we are good to go.